Good morning, team. Chemistry coach coming at you. Of course, when we're doing lab, probably the first thing we got to learn about is what we're doing, the scientific method. You've probably been through this talk in every science class you've ever had. Every professor talks about it, in a similar way. Some may have more steps, some may have fewer steps. Some may combine two steps into one step that some other professor does separately. Whatever. It all is the basic idea of how to think and discover. Right? You don't even need to use the scientific method in a science class. You could use it in an everyday scenario. It's just a thinking process. So our goal as chemists or scientists in general, is to understand nature and natural processes, right? Sky's blue, my arms pitch smell, whatever it is. We're trying to understand why. Welcome to the world and the mind of a scientist. Why? Especially chemists. We dig down to the smallest level going, why does it have that color? Why is this? You see all the whys? Kids are natural with this kind of thing. Hey, Dad, why is that? Why is this? And you're like, oh my God, so many questions. You got to love it, right? That innate curiosity of how the world works. So it's just a multi-step thinking approach to understanding natural process. Will we ever get there? I don't know, but we're getting better and better as we move along throughout the centuries, right? You look a century ago and it's like, wow, it's amazing how little we know. And maybe a century from now, they'll look back at us and go, wow, you guys hardly knew diddly squat. You never know. It's pretty crazy. I don't think we'll ever be done learning. So essentially, I'm going to break this down into 3 simplistic steps. A lot of people do 4, some people do 5 steps. Whatever. It's a scientific method as long as you get the basic idea. But all of them, no matter how many steps somebody teaches you in the scientific method, you have to start by observing something in nature. That's where the little kid is. Daddy, why is the sky blue? Why do crickets make that sound? Right? Dude, so many questions. I could go on and on and on. And they're trying to understand why. So this is the thinking process out. But very critical in chemistry to learn how to make proper observations. So we're going to spend quite a few labs learning how to do that. Because if you screw up the observation, your explanation of that will be flawed. See what I'm saying? So we want to be expert observers, crime scene investigator type people. And so pretty strict, my class, at least in my class, my labs, I'm very strict on how you do observations. But that's always the first step. And you can call that data, right? You're going to go in the lab, gather some data, but you wouldn't think about observing that like there's a tree there, the leaves are green. And it's hard to think of that as data, but technically it is. I'm just making an observation. And then I can go, well, why is that? Pretty obvious what the second step is going to be. Why? Trying to explain that. I'm going to stick in here, if you're one of the fortunate few discovering a natural law. Right? Where a law doesn't mean you understand it, right? So imagine the law of gravity, right? I can take this calculator, whoop, down it goes, right? I can take my cat, down it goes. It doesn't matter what system I'm studying. My cat, this softball, with all these kids' names on it, right? Whatever it is, I can just pick it up, boom, it goes down. Doesn't mean I know why, but I can see that consistent observation no matter what my subject is. Boom, it drops. There you go. That's a law where all systems or subjects you're studying all are impacted the same way. Law of conservation of that. There's going to be quite a few of these pivotal laws we're going to talk about. Law of conservation of mass. If you have 20 grams of reactants, you're going to get 20 grams of products. It's unavoidable. Law of conservation of energy. Laws of constant composition. There's a lot of fundamental and important laws that we will use as these cornerstones for chemistry. And we'll talk about those when we get to them. But doesn't mean you understand the law, right? It's just a set of data consistent with a bunch of different systems. So that's what we're going to include. I'm going to take another board and we're going to break observations. I'm going to go a little bit more than what's in a typical textbook because I'm going to relate this to lab because we do the scientific method in lab, not necessarily in lecture. So I consider this a lab thing. So when we're in lab, I'm going to break this into 2 types of observations and talk about what we're looking for and how we record that data in lab. So think of this as your first lab lecture. It has to come first. So let me get these 2 types of observations up on the next board, my friends. Right, the first type of observation, by far the most common you're going to do in the beginning part of many, many labs, learning how to make Measurements, right? You've been doing this since you were a little kid. Grab your ruler, a tape measure, blah, 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 weigh things, yada, yada, yada. It's just innately natural, I think, for us to do this. How long is that? How heavy is that? Blah, blah, blah. We call those quantitative measurement observations because they have a quantity associated with them. AKA a measurement. And you're never going to hear a chemist, or a professor come, let's go make some quantitative observations, students. Oh, have you made your quantitative observation? No, they're going to say, hey, go measure this, right? So it's called a measurement, but technically it's a quantitative observation because it has a quantity or a numerical value. This calculator has a length to it, right? What's the number? Anybody can do that, right? There's better ways and more accurate ways and less accurate ways. We'll teach you how to do that, but pretty straightforward. Most even young kids have a concept of that. But it's also have to have a unit. In chemistry, we got to watch out. I find a lot of students get sloppy and lazy with their units. If you don't put a unit on here, it's meaningless. Any measurement or quantitative observation without a number would be silly, right? How much does that weigh? Pounds. What does that even mean? Right? I need a number, but that's no different to me if I say, how much does that weigh? And you go, 32. 32 what? 32 megatons, 32 ounces, 32 nanograms. What do you mean? So a number without a unit is just as silly to me as a unit without a number. So you got to have a unit. And of course, uncertainty, this is the realm of the chemist. We want to know how, i.e. how many decimal places. If I have a specific measuring device, how many decimal places could I read that to? That's kind of the layman's terms for, uncertainty. Where there's a whole video on absolute uncertainty, how to take any measuring device, some graduated cylinder or thermometer, and go, can I read that to 1 decimal place, 2 decimal places, the ones place? Absolutely critical you learn how to do that. And so we'll be doing labs specifically on length. We're going to be doing one lab specifically on how to measure lengths and masses, temperatures, volumes. We don't have one specifically for temperature, but it's a huge majority of our labs are going to have temperature measurements involved. Lots of volumes all the time, masses. And so we want to get very, very good with our what's called accuracy and precision on these kinds of quantitative observations. Let's look at the other type of observation on the next board. The second type of observation is qualitative. So we have quantitative as a quantity and qualitative, just looking at the quality of substance. Of course, this would not have any numerical value to it or a unit or uncertainty. This is not a measurement. You're not going to grab a tool and measure it. All this is information on the quality of the substance. So like the color of my Hawkeye shirt, right? The odor of the cat litter boxes over there, right? So odor, color, the state or phase, is it a solid liquid? This is a solid. I'm breathing a gas, right? So just information that is just of the quality of a substance. You could think of like temperature. You could measure temperature as a specific value. It is, this liquid is 82.7 degrees Fahrenheit. That would be a quantitative measurement. But if you just say it's warm, that's a little more qualitative. See the difference there? Observations in my lab, both quantitative and qualitative, they're both equally of importance. A lot of people think measurements are more important than other things. No, they're all equally important, whether it's quantitative or qualitative. These are considered primary data in my lab. Primary meaning first. We record those first in our lab books, right? It's something you see or measure or witness. So if you ever see this little 1 knot symbol there, that means you missed the fact that that's primary data. In my labs, go with whatever your professor's doing at the time, but in my labs, we're going to use a non-erasable ink pen, preferably something dark, blue or black, because I like to grade in reds and purples and things. So blue or black would be great. Non-erasable on your data sheet, right? Make sure you don't do it on the back of your hand, right? Or try, some separate piece of paper that you lose or whatever. Record it directly in your data sheet or data table. But I like to use pen because I don't want you to be tempted to fudge your data, right? Especially for unknowns, you record some data, right? in pen. But if you did it in pencil and you calculate an unknown, and then I give you the true value, and you're like, ugh, I got like a 20 out of 50, that sucks. And you go back and erase some of your data and go, oh, professor, I just miscalculated something. I actually should have got a 50 out of 50. Like, yeah, right. Okay, I'm not going to accept that. I will personally not accept any primary data that's written in pencil because you could go back and change it after the fact, right? You got to be careful about the sanctity of your information. So do it in pen, right? Otherwise, I'm just going to, if it's in pencil, I'm going to erase it and go, that sucks to be you today. You got to go redo the lab and you lose points. Ho, 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 I'm such a hard nose, right? So you get it? Get it? Got a good pen. Blue or black, non-erasable for any primary data in lab. That's usually not covered in the scientific method, but that's our approach in lab. It's absolutely critical to do the first step properly. Observations, to me, are the most important step, because if you do that wrong, every successive step after that, just tank. So let's look at step 2. Now we have an observation. The innate natural response is, why is that observation the way it is? Why are those leaves green? Why does that smell like that? Why? We're going to try to explain why. Step 2, the hypothesis. All right, step 2, the infamous hypothesis. If your line of work is in step 2, you need to have a good self-confidence and a thick skin, because probably going to be wrong a lot. All right. This is our attempted explanation at the observation. Why? I said, my kids, why is the sky blue, Daddy? I don't know, because we have 5 cats in the house. It can be the silliest, completely wrong observation, but you have to prove that it's wrong. All right. Our goal is to make sure our hypothesis is correct. So we have to put it through testing to make sure it's not just a piece of garbage. You know what I'm saying? Because a lot of them are. I remember when I was getting my PhD trying to explain something, I spent years doing it incorrectly. I would think, okay, this is my research. This is an observation I saw. And I would propose, this is why. And then I would go test that for 6 months to a year and find out, nope, that was completely wrong. And then I'd say, all right, well, maybe this observation is because of that. Go test it for 6 months. Nope. That was an incorrect assumption as well. I was like, oh my God, it would take years and years to finally get a hypothesis that was somewhere right. So very commonly, a hypothesis is incorrect. That's okay. If you screw up 9 times, but get it on the 10th time, you got a paper, baby. You get a whole bunch of papers, you can get a PhD, right? Or you may end up getting a Nobel Prize. Who knows? You never know. Sometimes you might be sort of close. You're partially correct. Maybe bits and pieces of it are good. You just have to refine a little bit. So the main point about the scientific method is, we make an observation, we try to explain it, and then the third step, of course, we're going to test that. And just go through that process. I'll draw that to end this. I'll just draw that cyclic effect there. And just do it over and over and refine our hypothesis. I like this, but this didn't work, and let's refine it, or just dump it and get a new one. And we'll keep testing it and refining it over and over and over until it starts to explain a broader range of data or observations. You might come up with a great hypothesis that's been refined a few times, and get a call from somebody in another country, say, hey, I saw your paper and your little proposal there is explaining my results. You're like, well, that's cool. Hey, let's set up some joint project. Hey, blah, blah, blah. Scientific buzz. If you can refine it enough and test it enough, you may advance it and upgrade it to a theory. Once you've done that, you're in the immortal world of chemists, right? You get a theory named after you, you're immortalized, right? And we'll go through a bunch of different theories in chemistry and talk about the history of how they were determined and figured out through the scientific method. It's like a tennis match, between observation, people observing things, and people trying to explain things. Commonly, they're separated. When I was working at UCI, I noticed a lot of people were in the experimentalist section of scientists versus the theorists side. Right? So the experimentalists, like someone like me, I just jump in, banzai, plug my nose, just jump. Oh, I forgot to check that the pool was full of water. And I just start blasting stuff and gathering data. Blah, blah, blah. not bothering to think about it at all. I was more of a doer than a thinker. I was like, woohoo! And sometimes you'd have to sit back and go, oh, I got to think about what this means. Or you just give all your data to someone who's a theorist and say, what does it mean? And then they think about it and go, well, this is why. It's a great combination, but the ball's always going from the experimentalist to the theorist, back to the experimentalist, back to the theorist. And it's refined. It's an awesome, awesome way to get to the nature of things. So our goal is to get it upgraded to a theory. Let's look at step 3, my personal favorite, the experiment. All right, step 3, we want to test this hypothesis. Commonly, you'll get this in the real world as well. Someone will propose a hypothesis, they make a hypothesis to explain why something happened, and then somebody wants to prove them wrong. Maybe they got a personal vendetta. This has happened out there. They're like, yeah, your hypothesis is crap. This is total crap, and I'm going to prove it's total crap, right? Or maybe it's your buddy, and they go, I want to prove that you're correct. See what I'm saying? You can get there's personalities and everything. I've seen some pretty crazy little intellectual wars at the highest levels. But most of the time, people are working together to try to understand things. At UCI, we had Air UCI, which is this great collaboration between a whole ton of professors all over the world trying to understand things. It was an awesome, awesome deal. So what we're going to do is we're going to use the hypothesis to make a prediction about an experiment. We're going to run an experiment to test this hypothesis. So we'll create this experiment and say, well, if my hypothesis is correct, then these are the results we should get. That's your prediction. Some professors make that step 3. Sometimes they'll do observation, hypothesis, prediction in step 3, and then experiment. I just put prediction, experiment together. Whoop-de-doo, right? But anyway, we're going to predict the results of an experiment. Now, we go run that experiment, and we get data. We get results or data. We get more observations. Are those observations what you predicted? If it is, yay! Let's test it again and again and again and again, right? Just to make sure a hypothesis can withstand this experiment and this testing. But if we don't get results anywhere close to what we predicted, we go back to step 1 and go, well, our hypothesis was total garbage, so we discard it and come up with a new one. Or maybe we were partially right. We got some of the results we predicted, some we didn't. We're going, well, maybe there's something to our hypothesis. I'll just refine it a little bit. And then make a new prediction, new experiment, refine it, make a new prediction, new experiment. We just go through the cycles of the steps until that hypothesis can actually get upgraded to a theory. See the thinking process there? So what I want to do is just kind of put this all together and show you the cycle simplistically now that we got all the definitions and verbiage down, and we're done. So if you just want to see kind of how in general this works, obviously we make an observation, and then from that observation, we try to explain it with the hypothesis. Then we take that hypothesis, make a prediction about a particular experiment, and test it with that experiment. Run that experiment. That experiment gives you new data. You see the scientific method. Whether you do prediction as a 3rd step and experiment as 4th step, doesn't really matter. But we just go through and refine our understanding of nature until we feel like we understand it. And in the best scenario, we get that upgraded to a theory, right? That's our goal. Upgrade. Right? And this is your new data. Pretty straight. It seems so simplistic, but the best things in life, isn't that true, are simple like that? And boy, we are learning. The rate that we're learning in today's world is so accelerated compared to what it used to be a long time ago. It is mind-blowing. I don't know what the actual data is, but it just seems to me like in the last 10 years, we've probably collected more information than probably in the last 50 to 100 years. And it's accelerating faster and faster and faster, with the new forms of communication. Just an amazing, amazing world we live in right now. I mean, the world is at your fingertips. It's unbelievable. Imagine even 300 years ago, 200 years ago, 100 years ago, no internet, those kinds of things. I mean, 200 years ago, no internet, no cars, no electricity. I was like, oh, I mean, people have been living the same way for millennia. It's just crazy to think about how fast this information age has changed our lives. Some of you say for better, some say for worse. that's a fun conversation at a party or something. You know what I mean? But the chemists, right? We're trained to be non-biased and just say, hey, let's go through this obvious thinking process. Do not insert any bias into it. You can't want a particular result when you go into an experiment. You're not supposed to do that, right? You don't want to bias the outcome. You just, this is just the facts, ma'am. This is the data. Let's make the the hypothesis, test it, and if you don't like the results of that experiment, so be it. Welcome to science. I mean, you can run the experiment again and again, and if you keep getting the same thing, you're off, right? Deal with it. That's chemistry, and we just keep going until we get something that's confirmed, and then other people will confirm it. It goes through a peer review process. It's a fantastic method. Gotta love it. We're going to do a lot of this in the chemistry labs, but in general chemistry, we're going to focus mostly on the observation side. There'll be labs specifically for quantitative observations or measurements, lots of them, and some labs specifically just for qualitative, right? Doing different chemical reactions, trying to, see, did a chemical reaction occur? What were the signs you saw? What is the reaction? Balance it. Were there any patterns that you see, et cetera, making conclusions. Not too much in the hypothesis stage here, maybe an experiment here or there where you try to predict something. When you get to, if you're a chemistry major, when I got to like junior, senior level, the coolest parts, we got to design some experiments. I remember I got to make my own experiment. So I did one where I'm a coin collector, a coin guy. So I wanted to, look at the percent composition of certain coins, and I designed an electrolysis experiment for it. So I taught myself electrolysis, electroplating things, figured it all out. It was really cool and it worked. I was like, man, I was stoked. I actually did the whole thing myself. It was really, really neat. But again, for my class, we're pretty much focusing mostly on step one. We can do it, guys.